Okay, welcome to 3.1 Part 2, Investigating Quadratic Functions in Vertex Form. We'll start with a little warm-up to review yesterday's material. So, for each of the quadratic equations listed below, we're going to determine 6 of the characteristics. So, let's start with equation A, y equals 3 times x minus 1 all squared minus 3. So the direction of opening, this is always determined by the a value. And the a value is always the one in front of the brackets. So in this case it's 3. Now the width of the opening is determined by the magnitude of this, but the direction of opening is determined only by the sign. And this is positive, which means this parabola is going to open up. The width of the opening. Since this number is greater than 1, your y value will rise a lot faster than it would because we're multiplying every input by 3. So since it goes up a lot faster, it will be steeper and narrower. So in this case, it's narrow. Coordinates of the vertex, those are given by P and Q. P is always whatever comes after the minus sign, and we'll see how to deal with it when it's not a minus sign in the next one. And Q is all of what's after the squared. So here, coordinates of the vertex are just positive 1 and minus 3. Equation of the axis of symmetry, that is always the x value of the vertex, and it's an equation, so it gets an x equals, and the x value of the vertex was 1. The domain, this thing starts at minus 3, and it opens up, which we have already determined. So it'll be down here somewhere, and it will open up like this, and it will go on forever, infinitely upward. So it will never drop below y equals minus 3. So, oh sorry, this is for the range. It will never drop below y equals minus 3, so it will be y is greater than or equal to minus 3, but otherwise is an element of the reals. The domain, what x values are we allowed to input into this equation, this function, and your domain would be all real numbers. There's nothing we're not allowed to try to put in here for x, because the graph will go infinitely to the left and infinitely to the right. So let's take a look at equation B. The direction of the opening, your A is a negative value. This is A right here, and that will make it open down. The width of the opening, this value is between -1 and 1, meaning it will rise more slowly than one that was multiplied by a larger value. And since it rises more slowly, it actually opens wide. Coordinates of the vertex. If there's not a minus sign here, you could either think about it as rewriting it with a minus and then take everything after the minus sign, just like we did here. We take whatever's after the minus sign, so it was positive 1. Here we take whatever's after the minus sign, so it would be minus 3. Or you can simply think about it as flipping the sign on whatever you happen to see in the brackets. So your x coordinate will be minus 3, and your y coordinate will be q, which is positive 2. Equation of the axis of symmetry, again, always the x value of the vertex, x equals minus 3. The domain, whatever values of x we're allowed to try to input in here, x is an element of the reals. And the range, since this one opens down and it starts at positive 2, so your vertex would be right here, and it opens down, it will go infinitely down, and it will never go above positive 2. So y is always going to be less than or equal to positive 2. But otherwise, within that range, y can be any real number, so y is an element of the reals. Alright, so here's another example. Determine a quadratic function in vertex form when you're given its graph. This is really simple in terms of finding the vertex, but the a value is a little more complicated, and you'll see in a second that we will require the use of a second point in order to determine that a value. So right here we look at the vertex, and this value is positive 5 for x and negative 4 for y. So we will have something of the form y equals our unknown a value times x. Now since this is positive 5, it represents a shift 5 to the right, so it'll be x minus 5 all squared, and then it's shifted down, so that's minus 4, and that's all from our vertex of positive 5 and minus 4 right there. Now in order to determine the a value, all we need is one other point for which we know the y and x value, and we can plug those both in order to rearrange the equation and solve for a. So here's another point that's labeled on the graph. It is x equals 2 and y equals minus 1. So we have the ordered pair 2 and minus 1. We can therefore replace our y with the y value here, minus 1 equals a, and replace our x with the x value here, 2 minus 5 all squared minus 4, and then we try to solve for a. So negative 1 equals a, 2 minus 5 is negative 3, and we're going to square that and then subtract 4. So minus 1 equals a times 9 minus 4. Now in order to solve for a, we first add 4 to both sides, which will leave us with 3 equals 9a. And then to isolate a, we divide both sides by 9. So on the right side, the 9's will cancel each other and leave you with 1a. And on the left side, we can reduce that to our lowest terms fraction, 1/3. So a equals 1/3. Once we have our a value, we can go back up and substitute it into our equation. 1/3 times x minus 5 all squared minus 4. And using this equation, we can get every value that appears on this curve infinitely up and out. Alright, so curve B, we use the exact same strategy. This time we note that curve B opens downward, so this is going to yield a negative value for a. Other than that, we do the exact same thing. We find our vertex here, which is at 0. We haven't moved left or right, but we've moved 3 up. So your vertex is at 0 and 3. So we write y equals our unknown a times x minus 0 all squared plus 3. And of course x minus 0 is just x. So this will turn into ax squared plus 3. Now again, choose any other known point on the graph and substitute the x and y value into the equation to solve for a. So this point, labeled here, has an x value of 1 and a y value of 1. So we're going to substitute it in. So we go 1. So this comes from this coordinate. we go 1 equals our unknown a, and then our x value gets substituted with a 1, all squared plus 3, and we can solve for our unknown a value. Subtract 3, so this is negative 2 equals a times 1, which of course is just a, and there's our final a value, and of course our final equation is negative 2, and you can just go x squared plus 3, and here we don't actually even need the brackets. You can just write it as negative 2x squared plus 3, and as we predicted, because our graph opened down, it was concave downward, we ended up with a negative value for a, which is perfect, helps verify the fact that we probably did our work correctly. All right, your turn. Go ahead and give this a whirl. When you're done, you can unpause it and check your answers. So hit pause now and give it a try. All right, welcome back. There are your two equations. Hopefully you were able to come to the same conclusions. If you weren't, comb back through your work, try to diagnose your error, and see if you can correct it. Determining the number of x-intercepts is dependent only on two things, and that's the sign of your a value and the y coordinate of your vertex. So for all of these three equations, we will quickly determine the number of x-intercepts. For equation A, you can see that your vertex, the y-coordinate of your vertex is at -3, and the x-coordinate is at 0 because there's nothing in here in brackets with the x that gets squared. So your vertex is at 0 and -3, meaning 1, 2, 3, your vertex is going to be right there. And you see from the sign on A, this is positive, so this thing opens up. Now, since it starts below the x-axis and opens up, that means it has to have two x-intercepts. So let's take a look at B. This one opens up. It has an x-coordinate of the vertex. It's been shifted 1 to the right, but there's no q value, which means your vertex is at 1 and 0, meaning it lies right on the x-axis, right here, at 1. And this is positive, but in this case, since it's on the x-axis, it wouldn't really matter if this was positive or negative. It opens up, so there's only going to be one intercept. Similarly, if it was negative and had opened down, since it's on the x-intercept and on the x-axis, there would still only be one x-intercept for this one, and that's where the vertex is. So let's look at our third scenario. Here, your vertex is at -2, so again, you'll always flip the sign in the brackets with the x, and -1, meaning it starts below the x-axis. So -2 for x and -1 for y, starts below the x-axis right here. It starts below and it opens down because of the negative value of a. Since it opens down, it will never touch the x-axis, and there will be 0 x-intercepts. Okay, if this had been a +3, it opened up, there would have been 2, just like in this scenario over here. Similarly, if this had been +1 and it opened down, so imagine our vertex was here and it opened down, there would have been 2 intercepts as well. So it's all dependent on the values, the sign on A, and whether you've been shifted up or down from the x-axis. So here's another your turn. You know the drill. Hit pause, give it a try. Unpause when you're done. Here are your answers. Hopefully you are able to draw the same conclusions. Here's our last problem for the lesson. This is on page 156. This is the your turn. I would like you to go ahead and give it a try, and then when you're finished you can come back to class and we can check over this, or we can go over it together. So start by writing your equation in vertex graphing form, including an a value. So your vertex is going to be right here, so figure out how far it goes in the x direction and how far it goes in the y direction, and that all depends on where you decide to set your origin. Typically when I do this problem, I set my axes like this, and this is my origin at 0 and 0. So go ahead and give it a try. If you have any questions, come back to the classroom and see me, and we can discuss this one together. That's it for today's lesson. See you in class.